Good morning, everyone. My name is Ari Jenkinson, and today I'm going to be presenting my master's final, which is on 3D printed surface applicators for HDR Brachytherapy. My two supervisors are Dr. Pejman, Roshan Farzad from UWA, and Luke Slama from Sir Charles Gardner. So, cancer, a bit of background. Cancer is a leading cause of death worldwide, accounting for nearly 1 in 6 deaths in 2020, according to WHO. And in Australia in 2023, 3 of every 10 deaths are estimated to be from cancer. So another also fact is that we're one of the leading countries in the world for skin cancer, and skin cancer is quite a big problem, and we've tried to combat that with many things. So this kind of leads into our background from this. And of course, now going over some brachytherapy basics, is that sealed radioactive sources are placed within a close proximity of the cancer. So here on the right, we have a bunch of different, but the 3 main types are intracavitary, interstitial, and contact or surface. And in particular, mine is focusing on contact or surface, which is what we can see here on the right. It's also important to note the dose rate. So dose rates are quite important. So how much dose is being delivered. There are 4 dose rates, including pulsed. However, we're not going to talk about pulsed as it's not really relevant. Some examples of low dose rate is permanent seed implants, and high dose rate is commonly paired with surface or contact brachytherapy, which is what I'm doing. So here's the afterloader at Sir Charles Gardner. On the left here, we can see the backside of it with all the mechanics and how it works. Inside, the radioactive sources are placed, and on the right here, we can see this is how it comes out. The sources come out through these applicators and they're delivered. So hopefully this is kind of painting a picture of how this is all done with the middle photo as well. So to start with, we're going to talk about the clinically used bolus method at Sir Charles Gardner. Initially, the patient will be laser scanned to generate a 3D model, and the facial scan will be sent off to be milled at MTP, which is Medical Technology and Physics. The milled model is carefully marked where the applicators will be positioned, which we can see, or hopefully you guys can see here on the right. And then a radiation therapist will mold a layer of aquaplast bolus onto the milled face. They will then place the applicators, which are glued, and they'll try to follow the markings as close as possible. And then another sheet is placed on top, almost to sandwich the two in. The applicator and milled model are then CT scanned for positioning and planning purposes, and a mock treatment is performed to ensure there are no issues. A patient is brought in to have a CT with the applicator, and a treatment plan is created. And of course, the final step is patient receives treatment. So there are a couple disadvantages to this used. One, of course, is that it's prone to air cavities. Random variations of thickness because these molds are created by hand. Sources can get stuck, which is seen here on the right. There's too great of an angle at the bridge of the nose, and they have to work around these sometimes. Placement, so being able to position brachytherapy each and every single time is highly important. And milled plaster model dependent on MTP workload. So milled models can take days at times, depending on how busy or how backed up the MTP is. And optical laser also applies corrections to better complement the milling software. So a small amount of detail is lost in that step due to this. So this kind of leads me to some of my aims of my projects. So we're looking to improve the accuracy and reproducibility of source positioning to be within 0.5 millimeters, reduce these geometric and dosimetric errors, which is almost obtained from the accuracy. And we're going to compare this brachytherapy to other techniques, both EBRT as well. So 3D printed surface applicators, the steps are the patient will be laser scanned to generate a 3D model. The model and then we'll model and print the surface applicator from this. Really basic, no. And then of course it will follow the same steps. It's not this basic though. We're going to talk about how the model and how the surface applicator is, of course, created. So the patient fast scan data, which was used, which is the laser scan, I'll just quickly jump back here on the right, is done to the patient. So then we obtain an STL file, or this model of the patient. This file was then opened in Mesh Mixer, 3D designing software, and then a region of interest, which is far greater than the PTV, was drawn on the face. From this, we extracted it, and we actually took two different models. So we took an inner layer model, which was determined to be 6.375 millimeters, of an outer layer model, kind of like the sandwich idea, which was 19 millimeters. Once the models were separated into their own shells, Model A and Model B were then imported to Fusion 360. So the two models, the lower and the upper. So we put this into a CAD software known as Fusion 360, and a cross-section of the surface mesh model was derived as a reference geometry. So here we can see on the left is that this is what we started doing. We started creating these lines down, which is where the applicators should be going. And then from here, we have started spreading them out perfectly. So each one is exactly 12.75 millimeters apart. And this is because each applicator in diameter is 2.75, so we made each one 1 centimeter or 10 millimeters apart. And then this was applied the whole way across the model to ensure full coverage. And then, of course, we brought out these cross sections, and now we have created them and made them into 3D. So now they're actual tubes, and they're the actual diameter of 2.75. It's an important thing to note, in particular in the middle here, is that angles are important, which is what we were talking about in the start. So if an angle is too great, like in the bridge of the nose, sources can get stuck. And an angle that was found was about 55. So if we have less than a 55 degree angle, a source won't get stuck in the applicator. And because of this, we had to do some smoothing towards the top just to make sure that these sources would not get stuck. Overall, this doesn't really affect anything. It's just we can fix this step early rather than later. And it was important to know because that's what we did do. So now with these tubes, we're going to take it back into our older model, and then we're going to actually subtract it. So that's what B is. B is our tubes subtracted from our big model. So now we have these catheter channels, which we can use. And then we've imported this back into Mesh Mixer to make sure that this applicator fits smoothly over the scanned patient face. So this is what the final print looks like. Our final design is on the left, and then the middle is what was printed. And C is kind of a hollow, so you can still see those applicator channels and what happens. And overall, it was printed with an uncertainty margin of 0.05 millimeters. Everything was created in accordance with the Paris system, which is a common standard practice of brachytherapy. And applicator channels were allowed for easy insertion, so there was no problems with working with the afterloader and, of course, inserting the applicators. Overall, this print took about 8 hours, and the design for it, which was designed by a person familiar with computer-assisted drawing and modeling of the such, was done in under 24 hours. So this whole thing from start to finish took in under 24 hours. Important to quickly note is electron density. So HU values of PLA cubes were done. Particular, we did them at 100% infill. This is important to note because our brachytherapy plans work off TG43 assumptions. And our TG43 assumptions are that everything is homogeneous water. So PLA being slightly higher is just important to note. The reason that we went for 100% infill above homogeneous water was that we didn't want to create air gaps. We didn't want to have any variation. We'd rather have something that is solid. So here, back to the plans. Yep, it's made with Brachyvision using TG43, and of course, APPM consensus data. And this is what we got, and this is our plan. It's also important to note in our plan here on the Phantom is that this plan was created without care for dose to ORAs. So in particular, the eyes were not really considered. And as such, we try to focus on the greatest conformality to, or the greatest dose to the tumor. Another plan that was done was, of course, the bolus applicator. Unfortunately, I don't have any photos of the bolus applicator on the silicon phantom. I only have it on a patient, and this was the same patient that was used for our data. So as we could see here, a lot of air gaps, not only present inside of the bolus applicator, but also between the bolus applicator and the nose. We also did some EBRT plans, and of course, one of them was parallel opposed. So just two beams parallelly opposed. And of course, we did this. The plan also called for 2 centimeters of bolus, which is what you see on the right. And yeah, another one which was done or undertaken was 6 MV VMAP. So our VMAP plan was done. Our purple is of course our tumor, and we can see from the dose spreads where it went. And we also did 9 MeV electron beam, and same. So the way that we measured this, of course, was by film dosimetry. It's pretty standard. We used Galvtronic EBT3 film, and we followed AAPM TG235 protocols, which is pretty standard. We used the Epson 10,000 XL scanner, which is present at Sir Charles Gardner, and we followed this through by taking the red channels in MATLAB. So here on the right, we see our films, and what we're doing is we're taking a chunk of our film and we're doing the averages over that, and we're getting the pixel intensities over that. We're also taking the standard deviation over those for error bars. And on the left is how we did it. So of course you got left eye, right eye, and then we have just slightly to the right of the nose, which is where we try to place our films. In the middle is also our silicon phantom, which was what was used. So here are our results. Our results are quite good. As we can see here on the right-hand side, the 3D printed brachytherapy actually performed the best and performed the greatest. It's also important to note that we only did 1 fraction of each and every single treatment. So this is multiplied by the total fractions to receive a whole treatment dose. Each and every single one had to have their own film calibrated, apart from brachytherapy, because brachytherapy was done alongside each other with the same standard. So here's also some more data, just visualized in a different way. We can see the dose difference from the plans, and most of them performed under, whereas brachytherapy nearly pretty much conformed exactly to its planned treatment. We also have a percentage dose difference. We can see that clinical was about -20%. Most of them were about -20%. And there's also some interesting levels for eye doses. Most of them also performed under, apart from parallel opposed, which was a bit of a problem. So overall, our results for the 3D printed brachytherapy applicators, they improved accuracy, reproducibility, and reduced errors. And in doing so, we reduced costs of labor if we just have one department doing this all, I suppose. So it's important to also talk about the eyes dose. I kind of showed it in some earlier slides, but we'll actually talk about it now. So eyes and eyes dose is the main organ at risk here. It's really good to focus when we do these 3D printed superficial contact applicators to do it on the face, because the face is a very complex region. So if we can get this to work for the face, we can get this to work for simpler regions is I suppose a bit of the idea. So our left and our right eye lens are a bit high, especially for parallel opposed. It's a bit of an older treatment, and we couldn't necessarily get to have it. We couldn't necessarily get the plan to work as it was originally planned. So we're going to talk a bit about cataracts now. So what is cataracts? Cataracts is clouding or opacity of the normally transparent lens of the eye, which is why we focus on dose of the lens of the eye. So radiation cataracts is cataracts induced by radiation. And the ICRP, which is the International Commission on Radiological Protection, found that this threshold should be 0.5 gray. However, further studies done into the field almost tend to show that there isn't really a standpoint. There's more of an idea right now that there is considered two different types. One of them is considered early onset radiation cataracts. So the idea that doing high doses can lead to an early onset radiation cataracts, whereas most or if not all doses will eventually lead to radiation cataracts, but it is very hard to tell. But that's why we focused on our left and our right lens, because we wanted to explore this. However, in reading papers and doing literature reviews, it most likely will lead to it no matter what we do. That doesn't mean we should give up, though. A lot of interesting future work is in this field. I do believe that 3D printed brachytherapy is the future especially for surface brachytherapy. Just this year alone, a new type of shielding filament, which we see on the left, was created. Shielding filaments are filaments which are induced with heavy metals to basically do shielding. So it's very exciting. So imagine way back when with our apologies, sorry, I'll just quickly switch back to it. Imagine this, but we created a bit bigger, and we can actually also create shielding at the same time, and it has no additional time. We just have to flick a button on, and then we tell it to print on these regions to reduce dose. There has been some work done, and in particular, a Polish guy by the name of down below there, who I will not pronounce, he did some research into HDR 3D printed brachytherapy applicators with lead shielding, in particular over the eyes, where he took different spots on the face. And what he found out was that every single time, pretty much, the dose of the lens was reduced if we did use shielding, which is, of course, something that we should use if we're going to implement this clinically. Some other future work parts is that we do want to take some more data. So initially it was discussed to do an orthovoltage treatment. However, orthovoltage treatment proved we had problems basically obtaining data from it. We also don't have an orthovoltage unit at Charlie's, so we'd have to go over to Fiona Stanley and do it there. So there's a couple of problems with that. And another one is also, as the new era of 3D printed brachytherapy applicators comes in, is this Q&A for 3D printed brachytherapy. So 3D printed brachytherapy QA has a paper on it, which was released this year, and it kind of overlines what should be considered the normal for for anyone who's familiar in 3D printing, but it's very important for people who are not. And it's really awesome because this is now coming out this year, and all of these things, in particular 3D printed brachytherapy, are starting to move right now, whether it be with the shielding or whether it be with the QA. So everyone is very excited, and this is very much the next generation of brachytherapy. A final remark is that another thing we also want to get more data on is we also want to do another electron beam. So we did focus on a 9 MeV electron beam. However, a plan is to also do a 6 MeV electron beam, because we see here in this plan, we can see it's actually penetrating a bit deep, so it's not sparing as much normal tissue. We'd actually like to do a second round, and then we also do it with 6 MeV, just to get more data. Apart from that, I just want to say a big thank you to all my supervisors. Luke and Pejman both have been massive helps, have helped me walk through this journey of, I suppose, 3D printed brachytherapy. Been a real big help. Andrew for teaching me the basics. A lot of the guys over at the 3D printing cluster, which kind of now no longer exists. Yeah, just everyone involved with that. Riley, Andrew Lee also, and I suppose family, friends, everyone over at Medical Physics. Thank you very much. Apart from that, here are some references, and thank you very much for listening, everyone. Is there any questions?
Thanks, Ari, for the presentation. That was really good. Was there any questions for Ari? If you do, just pop your hand up and I can come to you. Martin?
Thanks, Ari. That's really good. Sort of interested in the electron treatment. So was that with a bolus as well? There seemed to be a bolus on the plan.
Oh, yes, very sorry. There was a bolus. I believe it was a 1 centimeter bolus off the top of my head, and that was used to conform more of the dose to the surface, because at the end of the day, we are treating superficial, a superficial tumor.
So was that one just made with the normal standard material? That wasn't a printed one, was it? Or was it?
No. So our Phantom, well, I mean, this is an electron beam, but our Phantom was created from silicon. So here in the middle.
Yeah.
And that is Aquapass. So it is 1-to-1 for water.
Right, that's Aquapass. Yep. And it was interesting in the results. You had the right eye. The electron dose was double, 100% different to what was planned. But I take it that was a fairly low dose anyway.
Yeah, I can pull it up over here on the right.
Yeah.
I mean, to the right eye, we can still see that
no.
it's still below. Yeah.
Yeah, the left one.
It still is important to know that it did deviate quite a bit.
Yeah. Yeah. I wonder if I'm not sure if you were involved in the planning, whether you know what algorithm was used for the electron dose calculation.
I don't. I think it was still the older. I still believe it was Eclipse. I think that's what's used, if I remember correctly. But it was an older version of Eclipse, as this was about 2 to 3 years ago when this was all taken. And now I know that we use newer dose calculations, in particular Boltzmann and things like that.
Sure. Yep. Thanks.
Ari, do you mind, on slide 29, I was just wondering how you calculated your error bars in the dose calculations there.
So in dose calculations, we did uncertainty bars based off, a lot of these were older models, so a lot of these used Monte Carlo simulations, and with Monte Carlo simulations came a hard number for our plans. With our parallel opposed, which is using a new method, I researched into a couple of papers, and I found a paper, and I used that, and that's kind of why, as you can see, the difference between our error bars in the old, our older data and our newer data. So parallel opposed is our most recent data and has also the smallest error bars. Yeah.
Okay, thanks. Were there any other questions for Ari? Roderick.
Yeah. Oh, my mic working?
Yeah. So
yeah. In terms of this bolus, are there any limitations in terms of minimum thicknesses that you could print if you did want a very thin bolus, or in terms of this 3D printing, what are sort of the limitations in that regard?
Well, I suppose the limitations of the 3D printed would be more so the limitations of, I guess, surface or contact therapy. Surface or contact brachytherapy, you don't really want to ever go or try and treat anything below 5 millimeters, below skin depth. So I suppose you could have a really, really thin base, but at the end of the day, we can only treat so far with this brachytherapy anyway, which is why it's used for superficial treatment. So I suppose you could have a really fat base and then barely have dose to the very, very top of the skin, but it depends on the treatment, really.
Great. Were there any other questions? If not, I think we'll leave it there. Thanks, Ari, for the great presentation. If you don't mind, I'll stop sharing your screen. I'll stop the recording.